So the goal for today is for us to build up to the fundamental group, and then in the next lecture we'll go into more detail. But the hope is by the end of this hour, we'll see a definition of the fundamental group, right? But before we get talking about the fundamental group, which is this way of taking some topological space, a shape, and translating it into an algebraic object, a group, let me just remind you what I mean by group. So many of you have taken some kind of group theory before, but if not, let me just remind you of what a group is, or introduce you to the idea of group. A group is a set, I'll call it G for group, with a binary operation. So what do I mean by binary operation here? You should think it's something like times or plus or something analogous. I'll denote it by dot, where by binary I just mean it takes two elements of the group, so something in the group and something else in the group, and spits out a single element in the group. So addition does this, multiplication does this. Right, these are binary operations. So it's a set with a binary operation that satisfies three properties. Maybe for those who have taken group theory before, you can remind me, what's the first property of a group? It should have an identity element, okay? So there's an identity. So that just says that there exists some special element of the group, as noted by little e, some special element of the group, such that if you take any other element of the group, let's call it A binary operation with E should be just A, or E binary operation with A. It doesn't matter which side you do it on, you remain at A. And this is true for all A, for all elements in the group. So you should think this is like an analogy of the additive identity. If you add 0 to anything, it stays the same, or the multiplicative identity. If you multiply 1 by anything, it stays the same. Okay, so an identity, what else? Okay, there should be inverses. And so this is going to say for every element of the group, there exists some other element of the group, some other element B, although here I'm going to go ahead and spoil and tell the name of it, A inverse. There exists some other element which we're going to call A inverse in the group, such that a binary operation with A inverse is the identity element, or A inverse binary operation with A is the identity element. So I'm not assuming this is commutative. Many operations like addition and multiplication are commutative when you're working with numbers, but you know, like the multiplication of matrices isn't necessarily commutative, right? So, you know, there are some spaces where this operation may not be commutative, and that's why I'm stressing on either side these relations should hold. And what's the last property we should satisfy to be a group? Yeah, you need to be associative. Associative. Which is just saying that for any three elements of the group, A, B, and C, if you first combine A and B by a binary operation, and then you combine that with C, that should be the same as A combined with B and C. And this is for any three elements, A, B, and C of your group. Commutativity isn't one of them, right? You don't have to have a commutative binary operation, but it does need to be associative. Okay, yeah, you're probably noticing the drops of water falling, so that makes life fun. We'll just dodge them while lecturing about groups. So let's give some examples of groups. Let's give some examples. The integers, so Z here denotes the integers. This is just the negative numbers, -2, -1, 0, and the positive. So the negative and positive whole numbers, including 0 and 0. With what binary operation? Which one? Addition. Yeah, so this set with addition forms a group. So why does that form a group? Well, what would be the identity here? Your identity is just 0, because if you add 0 to any integer, it stays 0, right? And then you can double check that there are inverses. What's the inverse? What would be like the inverse of, what would be like the inverse of 2? This is weird notation, but what would be the inverse of 2? -2. So, kind of using weird notation here, but I'm just saying that if you take any number like 2, there's some other number like -2, so that 2 plus your -2 gives you your identity. Or your -2 plus your 2 gives you your identity. And we know addition is associative. Okay, you said addition. How about multiplication? Does this give you a group? Is there an identity? Yeah, there's an identity. What's your identity for multiplication? Your identity would be 1, because 1 times any integer is itself. But why are you saying it's not a group? No inverses, right? Like, what would be the inverse for something like 2? What would be 2 inverse? And it's like, well, 2 times what gives you the identity? Gives you 1. And it's like, well, you know what it is. It's 1/2. But 1/2 is not in your group, right? The problem is this guy is not in Z. Is not in Z. So this is not a group. This is not a group. If I really wanted a group with multiplication, what would I need to do instead of Z? What's that? You might be tempted to do Q, but what's the problem with Q? 0 doesn't have an inverse. So now you might be like, well, what if we do Q without 0? Is that going to work? It works for multiplication. Q without 0 in multiplication works. But Q without 0 in addition doesn't work. Because there's one more property that I kind of implicitly said here, which was right here. And that is you should be closed under your operation. So when you combine two things, then you get out. If you do Q without 0, and you try and do addition, 1 and -1 gives you 0, that's a problem. Because we said 0 shouldn't be in there. But yeah, this here you could, if you wanted a group, you could have as a group something like Q omit 0, which is sometimes known by Q star, which is just Q and omitting the 0 element with multiplication. And that would be a group. So this is a group. Okay. Let me talk about, I don't know, maybe some other groups. How about this guy? 2Z. Do you know what I mean by 2Z? 2Z, by this I just mean the set of 2 times the integers. So 0 remains 0, 1 becomes 2, 2 becomes 4, 4 becomes 6, -1 becomes -2, and so forth. These are the even integers. And what operation can I use on there? Addition. Yeah, addition is my operation. And notice it's closed. So if I take any even number and add to another even number, it remains even. So it's closed. And you can check that it satisfies, just like before, 0 is your identity. And make a positive number a negative, it's still even. Make a negative number positive, it's still even, right? So moving your sign doesn't change evenness. So you still have inverses just like you thought. The inverse of 6 is -6 and so forth. So that's another group. And once you start having a couple of groups, you can define maps between groups. So a homomorphism is a map between two groups from G to H. Oh, homomorphism. So the etymology here is morph, transform, map. Homo, same. So it's a map that's keeping something the same. So what is this keeping the same? The map from G to H. It's a map between groups that respects the binary operations. As follows. F of some guy in G, binary operation with F of some other guy in G should be F of the first guy in G, binary operation with the second guy in G. So there's a couple things to make clear here. Here my A and B are elements of G. Here this binary operation is a binary operation between these guys. And where do these guys live? Those are on H. So this is a binary operation on H. Whereas this is the binary operations taking place in G. Now, if your example is like a map from Z to 2Z, so example, there's a map from Z to 2Z. These two groups both have the same binary operation of addition. So you would just do addition in both cases. But you might be moving from a group that has one binary operation like addition to another one like, say, multiplication, if multiplication is valid for that other group. What would be an example of such a homomorphism?
Send 1 to -2. And,
You said send 1 to -2? You're just trying to be complicated. What is the natural? Yeah, okay. Yeah, it's like,
twice the input.
Like some men just want to see the world burn, right? So you send A to like 2 times A. You could also send A to -2 times A. That would work as well. You know, and you can just double check this now. So like double check that this relation holds. You would just be like, okay, you know, what is F of A times F of B? And then we need to compare that with F of A, B. Oh, I said times, but the binary operation is actually plus, right? So this would be 2A plus 2B, whereas this guy is 2 times A plus B, right? But those are in fact equal. So this one works. You could also do -2 here. That would just become negative, negative, and negative, and that equality also holds, right? So you can check that it's a homomorphism. Okay. In fact, this homomorphism is quite nice because this homomorphism happens to be a bijection. Right? There's exactly a 1-to-1 correspondence, right? And it's surjective, it's injective, and surjective. So everything in here, like 3 maps up exactly one thing here, like 6. You don't have 2 guys being mapped to the same thing. So you have a bijection between these elements and these elements. When you have a bijective homomorphism, we call that so if it's bijective, what do we call it? An isomorphism. Isomorphism. Why isomorphism? This is a map. Iso means same. Homo also means same, but iso means same in kind of a stronger sense, right? Something stronger is remaining the same between these two groups. And maybe I'll just give one last example. This is a crash course in group theory of a group to show you something that's not isomorphic to Z. And that's going to be the group that I'll denote by Z sub 3. Z sub 3 is going to be the set that just contains 3 elements, 0, 1, and 2. If you wanted to, you could write 1, 2, and 3, but I prefer 0, 1, and 2 because this is going to be suggestive of what is my group operation. What kind of addition? Yeah, if you just say addition, it's not closed because 2 plus 2 is not 4, and that's not in this group. But if we do as my operation addition mod 3, now we have closure, right? So, you know, for example, 2 plus 2 where you're doing this addition mod 3 would just come out to be 1, because we're doing it mod 3, right? That's right. So now we have this nice binary operation on that group. And you can define a map. Let's use F again. You can define a map, say from Z with addition to Z3 with addition mod 3. What should this map here be? What's a natural homomorphism? What's a nice homomorphism between these? Yeah, it's just the mod 3 map. So you're just going to send whatever this n is to whatever n mod 3 comes out to be, right? Sometimes, so what's going to go on here? Here you're going to have something like 17. So for example, 17 is going to get sent to, 17 is 1 less than multiple of 3, so it's 2. Right, it's 2 more than 15. So it's 2. Okay. Sometimes you write these guys 0, 1, and 2 with little brackets around it to represent that each one of these is a class. And 2 is the class of everything that's equivalent to 2 mod 3. 2 mod 3. So 17, 7, no, not 7, 8, negative 11, lots of stuff in there, right? Okay, this is a homomorphism, but it's not an isomorphism. It's clearly not bijective, because as I just pointed out, something like negative 11 would also go, is that true for negative 11? No. What's a negative 11 mod 3? 1. Right? That's how math works. Negative 10. Negative 10 mod 3 is 2. So this is clearly not injective. So this is not a bijection. So these are not isomorphic. It's a homomorphism that's not an isomorphism. And you kind of know it's not an isomorphism because there's like a whole lot more guys in here than in here. Right? This only has 3 elements. So we didn't prove this, but maybe if there's a bijection between 2 sets, they have the same cardinality. And these have different cardinalities. Okay, that was our crash course on group theory. Yeah, please. Oh, I'm sorry. When I say bijection, I just mean 2 things. It's both an injection and a surjection. But if those words are, Latin to you, or maybe Greek, or I don't know what the etymology of these words are, injection just means 1-to-1. This is not 1-to-1. It's several to 1, because I have many different things that go to the same value. 1-to-1 is I never have more than one thing get mapped somewhere. And surjection is sometimes called onto. You hit everything in the image, right? Any number you pick in 2Z, something's going to get sent to it. So bijection just satisfies those 2 properties. Just means they match up nicely. They match up. Nothing is missing, nothing is not hit, and you never have 2 guys getting mapped to the same thing. Okay, so that's some crash course in group theory for you. So store that in your minds, and now let's step back into the land of topology. So here we are jumping back and forth between algebra and topology, but by the end of this class, we want these 2 worlds to collide with something called a fundamental group. But stepping back into the land of topology now, let me remind you what a homotopy is. So we discussed homotopies in the last lecture, but I'm going to focus specifically on a homotopy of a path. So a homotopy of a path is just a map that takes the interval and maps it into some space, some series of maps f of t. So you should think maybe your f of 1 looks something like this. And then maybe f of 1/2 looks something like this, where here my t is going to vary from 0 to 1. So you have some path at time 1. Oh, I should start at 0, shouldn't I? Some path at time 0, some path corresponding to time 1/2, some path corresponding to time 0, and everything in between. There's some path for f of 1/4. Oh, sorry, there's f of 1. Oh, we're going from time 0 to time 1/2 to time 1, and everything in between, right? Now, I want to do this in a way that it's continuous, so that if I drew like f of 0.1, it would just be slight variation of f of 0. Or maybe a significant variation, but then in between those slight variations, right? So when I just move time a little bit, this thing deforms continuously from 0 to 0.1, 0.2, 0.3, 0.5, all the way up to 1. So a continuous movement from one path to the other. So a homotopy of paths is a continuous family of maps from time equals 0 to 1. And typically, and I'll just make this the convention for the class, when I talk about a homotopy of paths, I'll have fixed endpoints. Which just means that no matter what time you're at, the thing that stayed the same at all times were these two endpoints. All the other points can move and slide along, but the endpoints stay the same. And so the way we write that is we say at all times where the path begins is going to be at some point x0, and at all times where the path ends is going to be at some point x1, x0, x1. Is that good? Okay. See, now I've primed you to talk about groups, and so secretly in the back of your mind, you should be thinking like, how are we going to end up talking about groups? But it's coming. Let me just say a few more things about these homotopies. Let's just make some observations about them. If you're in a space like R2, then I claim that if you take any two paths that have the same endpoints, if I take any, I'll call this F0, and any F1, as long as they have the same endpoints, as long as my F0 times 0 is this point x0, which is the same as my F1 at time 0, as long as these both start at x0, as long as they both end at time 1 at x1, then I claim there's a homotopy between them for any two paths you can imagine in R2. And I should really stress, like, these are any paths. You know, this path could have done some very different things. He could have even like done like a little loop-de-loop. Ooh, you know? Here's my new F1. But I claim, I didn't say these paths were embeddings, so they're allowed to cross themselves, right? I never said that the path was an embedding, it's just a map, so it's allowed to cross. An embedding would not allow it to cross itself. When I say something's an embedding, it means it doesn't cross itself. But here it just maps into R2. And I say there's some way to deform this guy into this guy in a continuous way. And maybe that's not too hard to see. You can just imagine like if you had pieces of string, you could start dragging this piece of string until it lined up with the other piece of string. But you can actually give an explicit formula for the homotopy. I want an explicit formula for how to move F0 into F1. That is, I can give an explicit formula for what this homotopy should be at any time s. So there are two variables here, right? One t is describing which path we're on, the 0th path all the way up to path 1. And the other S is describing how far along the path you are. Right? So tell me, what is the explicit formula? Yeah?
T times F0S plus 1 minus T times F1S.
Very close. I think you got it backwards. If you want to begin at F0 and end at F1. That would also work if you just do it in the reverse. So let's think about why this works, right? So I'm at some point S here. So this is like time S. Maybe my S is like a quarter, you know, maybe here it's about a third or something, about a third. Whatever it is, you had some time S on here. And there's some corresponding when you have time S over here, you know, you're like something like that. But this is going to describe how this single point S moves from here to here, and this is just an equation of a line. This is a linear relationship in T. So this is keeping track of what S is at each time interval, where T, the other time now is T, where your T is going from, say, 0 to 1. And so it will just keep track of how this point moves. And then, you know, you'll have some other value for S over here, and it'll have some corresponding value, I don't know, maybe down here, and that's also going to follow a line. And every point will just move along a line, you know, over here, it will follow some line to, I don't know, something over here. Everything will move along a line, but the result is if every point moves continuously, then the whole line moves continuously. Okay, so why does this work? Well, think about what this is when T equals 0. When T equals 0, on the right-hand side, you just have 1 times F0 of S plus 0 times F1 of S. Notice at time 0, this just becomes F0 of S. At time equals 1, though, this instead becomes 1 minus 1, so it's a 0 on the first term, and a 1 on the second term. So at time 1, you're just at F1 of S. And at any time in between, you had some linear relationship between those points. Where we're thinking of this in R2 is just like coordinates, right? So you would be able to find exactly where you are. Like at time 1/2, you're the average of those 2 points. Or you'd be at the point directly between them. So at time 1/2, you would be exactly at this point in the middle on each one of these lines. Okay. So this trick always works in R2. So in R2, any two maps, any two paths are homotopic as long as they have the same base points. So here we have this homotopy, so we write that F0 is, as long as they have the same endpoints, is homotopic to F1. You could also do the same argument in R3, or R4, or N. Or in general, you can make this argument for any concave space, where the definition of concave, so for any concave space, because the definition of a space being concave is just given any 2 points in the space, the line connecting them is within that space. Sorry, I was just teaching calculus. Of any convex space. So what's an example of a not a convex space? You know, like what's a space that's not convex?
Letter C.
Okay, I'll make it like a bubble C. You could just do a single letter. But this is clearly not convex because if you take 2 points, the line connecting them passes outside of the space. And so this would require you to homotope like outside the space, which you're not allowed to. You know, all these f of t's have to remain inside of your space at all times. But in general, it just means that if you're in any space that's convex, you know that any 2 paths, as long as they have the same endpoints, are homotopic. And for us, we only talk about homotopy for things with fixed endpoints. For paths. We happy? Yeah. Okay. So I should make a quick technical observation. Which I know some of you already started thinking about in the problem set, but let's just do it here. I could write this as a lemma or proposition. Homotopy of paths and from now on, just understand I always mean fixed endpoints. Homotopy of paths with fixed endpoints is an equivalence relation. Okay, so what do I mean by equivalence relation? Well, we remind ourselves of the definition as we prove it. An equivalence relation is a relationship that satisfies three properties. What's the first property? It should be reflexive. What does it mean to be reflexive? Well, you should think like the paragon of equivalence relations is equals, and reflexive is just saying something equals itself, right? In this case, we're saying the homotopy of paths is reflexive, so we're saying that any path should be homotopic to itself. Is there a homotopy that takes a path into itself? What's the homotopy? How should you define this homotopy so that it starts off at f and ends up at f? Just define it to be constantly f. So at all time, for all s, he's just identical equal to whatever f of s is. So this is just constant, not in the sense that everything gets sent to the same point, but constant in the sense that at all times he remains f of s. So I don't mean to constant to confuse you. It's not saying the path all to one point. It's in all times you just stay fixed there, right? This is kind of a dumb homotopy, but there you have it. The second property is that it should be symmetric. So in the case of equality, we say equality is symmetric. That means if A equals B, then B equals A. Symmetric here is we're going to assume, suppose that you have some homotopy from f0 to f1. So via some homotopy f of t. So f begins at 0 and ends up at 1, where your t is running from 0 to 1. Now what I want to argue is that I could start at f1 and there'd be some homotopy that takes me to f0. So what is the homotopy that begins at f1 and ends at 0? What do you call it? Yeah, f of 1 minus t. Very good. So this is how we'll define this guy now. Because notice, when time is 0, he just starts at f1. And then as the time approaches 1, he approaches f0. So this is just running this one backwards. So this is just doing it backwards. Okay. There's a third property. Not sure if we have room for it. Well, hopefully we do. I think we can squeeze. If we need to, we'll come up here. What's the third property? Yeah, transitive property. That's saying if A equals B and B equals C, then A equals C, right? In this case, with homotopy, suppose, let's say f of 0 is homotopic to f of 1. G of 0 is homotopic to G of 1. And your f of 1 is your g of 0. So sorry, I had a little bit clumsy notation there, but let me try to help us see a picture of what's going on here. So the picture is your f of 0 might look like this, runs until he is at f of 1. So there's some homotopy from f of 0 to f of 1. And then your g of 0 happens to align with f of 1. So your g of 0 happens to be equal to f of 1. And he runs until he's at some g of 1. And we know there's some homotopy from f of 0 to f of 1. And we know there's some homotopy from g of 0 to g of 1, some way of deforming until you get to g of 1. We want to conclude there's a homotopy from f of 0 to g of 1. So we want to say, then there's some homotopy, so that makes f of 0 homotopic to g of 1 via some homotopy h of t. So what should h of t be?
Piecewise. So first go from f of 0 to f of 1 by multiply going twice as fast.
Okay, so my f of t, this is very good. You first wanted to run the course of the f homotopy, and then we wanted to run, good. And then we wanted to run the course of the g homotopy. But now we're going to have to adjust these times, because you wanted to run the course of the f homotopy in just half the amount of time, right? So not when time goes from 0 to 1, you want to do all of f of t in half the amount of time. And so in order to go from 0 to 1 in half the amount of time, we need this here to be f of 2t. Now he'll run this first homotopy in half the time. Now he still has half time left, time going from 1/2 to 1 to run the second guy. But what should the equation here be? So it starts off at 0 and ends at 1. Yeah, if you do 2t, he's going to be 1 to 2. So then we need to shift 1 to 2 to 0 to 1 by putting a -1 in it. So by just adjusting these times, we can explicitly define a homotopy that first does as the first half of the homotopy, it's the f homotopy. As the second half of the h homotopy, it's the g homotopy. And now we have a single homotopy defined as piecewise ray. So this is an example so I'm going to talk about a little bit more in a few minutes, which is essentially reparameterizing, right? Just adjusting the speed at which it runs through it. Okay. Cool, we're happy the homotopy path is an equivalence relation? Okay. So since we have this equivalence relation, sometimes I'll use this notation where I'll denote by bracket f everything that's homotopy equivalent to f. So I'll denote by this the equivalence class. That is to say, equivalence. Yeah, sometimes a few letters get left out, don't they? That is to say that if I have two maps that happen to be equivalent, let's say I have some f that happens to be homotopy equivalent to g, that's going to be the same as saying the equivalence class of f is equal to the equivalence class of g. So take a second to digest this. This is the class of everything homotopy equivalent to f. This is the class of everything homotopy equivalent to g. If f and g are themselves equivalent, then the class of everything equivalent to f is the same as the class of everything equivalent to g. And the analogy you should think about is like this mod 3 arithmetic, right? So the analogy you should think about is when you're working mod 3, you have things like 7 is equivalent to 2 mod 3. So if you think about the set of everything that's equivalent to 2 mod 3, that's the same thing as the set of everything that's equivalent to 7 mod 3, right? So this is the analogy. 7 is not equivalent to 2 mod 3. Oh my goodness. 8 is equivalent to 2 mod 3. So numbers are hard, right? But 8 and 2 are equivalent mod 3. So if you've seen some modular arithmetic before, that's the same as saying the set of everything equivalent to 2 mod 3 is equal to the set of everything equivalent to 8 mod 3. Good. Okay, so when you see two equivalence classes being equal, in your mind you can just parse that as, this particular map is homotopic to this particular map. You can move back and forth between those. Okay. So now that we have this idea of equivalence class, what is the equivalence class of homotopies with endpoints like x0 and x1 inside of R2? Like, how many equivalence classes are there?
You're referring to specifically between x0 and x1?
Yeah, between x0 and x1, how many homotopy equivalence classes are there? Just one, because everything's homotopy to each other. Right? So there's just one class. There's the class, there's just a single, there's just one here, there's just one homotopy equivalence class. Homotopy equivalence class. There's just one. Because everything is homotopic to everything else. So any F0, F1, whatever you can think of, they're all going to be equal to each other, homotopic to each other in R2 or any other convex space, as long as they have the same base points. But that's not true in all spaces. So can you think of a space where that wouldn't be true? Where you might have a couple different equivalence classes? The torus? Yeah, the torus is a really good example. It's actually kind of a complicated example, so let's hold on to that one for next week. Give me one slightly simple, Larry. Yeah, let's think of an annulus. That's the one. You see, when I ask a question, it seems open-ended, but I'm actually fishing for a particular response. And if you don't say that response, then, so here I have an annulus. So this is just the circle thickened up a little bit. 0, 1, it's the circle that's been thickened up a little bit. Let's pick some base points. So I don't know. Let's just make them really simple. I mean, just put one of the base points over here, like x0 will be on this side, and x1 will be on this side. And we claim that there are some maps not homotopic to each other. So give me two paths not homotopic to each other. Yeah, like happiness and sadness, right? Like these two paths are not homotopic to each other. If we call this path the path F and this the path G, then at least it doesn't seem like, maybe, I don't know, how, you might think there's some way to slowly move him up, but the problem is you move him up, you still have this stuck down here. And so this isn't a proof. You should just have a very strong intuition that there's no way to move F continuously onto G, leaving the base points the same, without leaving the space. There's no way to do it inside the space. We'll prove this next week. That's one of the first things we'll look at. But at least now you should have a very strong intuition that your F is not homotopic to G, which means that F and G represent distinct equivalence classes. There's other things inside of the equivalence class of F, right? There are other things that are equivalent to F. What is something equivalent to F? Well, maybe this guy that just goes this way for a bit, but then he's like, oh, I'm not going up there, and then he comes back down, and then he does a little woo, and then he ends up there, right? There is a way to deform this guy into F, so maybe I'll call this F prime. I kind of hate that notation, but that's okay. We can move F into F prime, so F's equivalence class is the same as F primes. That is to say, F is homotopic to F prime. There's a way to slide the F up a little bit. Yeah? F is not equivalent to G. They're not equal. Thank you. Thank you. They're not homotopic. Very good. Okay. Good. So what is this line by Humpty Dumpty? It's like when I say words, they mean precisely what I intend them to mean. So here it's like, when I write, don't believe what I wrote. You know, it's like, believe what I intended to write, right? Okay, so hopefully we believe this. I want to make these examples a little bit more extreme and dive into a little bit deeper, but to do that, I want us to move from thinking about just paths to thinking about a special kind of paths, which are loops. Whereby a loop is just a path f that maps 0, 1 onto some space where, well, what should it be? What should be the condition? You tell me. Yeah, it begins where it ends, so where your f at time 0 should be equal to your f at time 1. Right? And so there's just one point called x, call it x0, one single endpoint. The beginning endpoint and x0 and x1 are the same, so let's just call it x0. And this is referred to as the base point of the loop. So instead of two endpoints, you have one base point for a loop. Now, if we think about loops, in R2, the story is exactly the same. That I can take, you know, whatever base point I want, call this my base point x0, and you can draw some loop, and then someone else could draw some other, and loops can do little, you know, weird behavior or whatever, that's fine. And there's some way to deform from one to the other in R2, and any other convex space. So exact same story, you still have just one homotopy equivalence class. But let's come back and think about the annulus. And let's think about loops in the annulus. So I want us to think about loops in the annulus. So I'm going to erase R2. And I claim now we have actually several different equivalence classes. So let me draw a couple different annuli. And with these different annuli, maybe we can begin thinking about what some of these equivalence classes look like. Okay, so you know, in each one of these, I'll draw my base point. So here's my x0 in each one of them. Okay, what's one thing my loop might look like? It might just go around it once, right? So you might have a loop that just goes around once, right? Okay, good. We should specify direction. So let me put some arrows to say I start here and go around this way. Now, that guy in this equivalence class, so this is going to represent an equivalence class, would be the same as this guy, who doesn't really quite know where he wants to do in his life. Kind of, you know, oh, I don't know, maybe I'll study math, maybe physics, or should I go into finance and sell my soul? I don't know. But eventually, you know, comes around and gets a math degree, right? So there's another one, and those are equivalent. So those are homotopy equivalent to each other. The blue one is a little bit more straightforward. This is the kid who was like, you know, doing math Olympiad problems when he was 8 and whatever. So we're going to call this guy, I'll just call him W1 for winds around once. And this is going to be my representation of the equivalence class of things equivalent to W1, the guy who winds around once. What else might you do? Okay, so I saw you do a motion that looked like you were winding around once, and then again, right? Something like that. So bam, 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 bam. Let's call this W2. W2. Now, we haven't shown it, but you know in your gut there's no way to change W1 into W2. We'll have to show this next week, right? Here I'm just trying to give you motivation for this definition, so it's a little more concrete. But like, you should know in your gut, like, there's no way this guy is going to become like you can try to start with how, to get him, you have to pick him out of the space, twist him, put him back, right? There's like no way to do this in the space. And we'll have to justify this, but hopefully you have an intuitive vibe that these are not equivalent. So you tell me, here are two equivalence classes. Can you think of any more?
No winding.
No winding. Okay, so what might that look like? Well, in the extreme case, it's just constant. So like W0 could just be constant. Or what else could it do? You could, here's one. You could go like, never mind. Right, you could do that. Or in fact, you could go all the way there, but then turn around and come back. So you could go all the way around and seemingly completely W1, but then you keep moving. You only have half time. And then the rest of your time you just go back. And you undo everything you did. So that would also be equivalent to W0. Okay. 0, 1, 2. There could also be you could wind around 3 times, or 4 times, or arbitrarily many times, right? So right now we have 1 for every non-negative integer. What else might we do?
Go the opposite direction.
Yeah, you could wind, but in the opposite direction. So here I was winding clockwise. But I could instead wind. Oh, okay. I might change our convention next week. Well, I'll call this negative and this other one. But who cares? Once you have a convention, we'll follow it. Where you go this way. Because typically we think of that as positive, right? Well, okay. For today, we'll think of this as the negative direction. In which case, this would be W of -1. Or you could wind around twice in the negative direction and so forth. You could have W of -2, W of -3, and so forth. Which means, if you think about the set of equivalence relations of loops in the annulus, if you think about the set of equivalence relations, it really seems like you have one corresponding to every integer. It seems like this set of equivalence relations looks a whole lot like Z. Right? It looks a whole lot like Z, 1 with each integer. I said the goal for today was to build up to the fundamental group and not get leaked on. We almost have this notion of how, given a shape, there's a group. But this isn't a group, this is only a set. Given some space, you can ask, what is the set of equivalence relations? It gives you a set. What else do we need to form a group? A binary operation. We need some binary operation that's going to give us a way of combining loops. So, how do we combine 2 loops? Let's pop over here for a second. And think about a binary operation, which will just be our way of combining 2 loops to get another loop. Or let's step back for a moment and just think more generally, if I had 2 paths, how can I combine 2 paths to get another path? So if I have 2 paths, F and G, that are both paths sending 0, 1 into some space, how do I combine them? Well, if your F happens to say begin at x1 and end at begin at x0 and end at x1. And if your g just happened to align so that g started at x1 and finished at, I don't know, let's say x2 as its endpoint. If they happen to align so that in particular my f at time 1 equals my g at time 0, then there's a very natural way to stick them together. I can just define f dot g, which is sometimes called the product of the paths, to be equal to what? Well, the thing that first travels along f and then travels along g. So this is given this condition. You can define this so that at time t, this will equal piecewise definition. We want to travel along f at double speed. So for t going from 0 to a half, he should just travel along f at double speed, and then he should travel along the path g at double speed. So from time 1/2 to 1, he should travel along 2t minus 1. And that will give you a definition then for the product. Now that's what it is for paths. In the special case of loops, as long as your two loops have the same base point, then you satisfy this condition, right? Because you just have some base point, you could even just call it x, or keep calling it x0 if you like, where you're just going to go around and do whatever you do. And then you come back to x0, and then you start doing, so like, let's call this your f, first loop f, and then you go and you do your g loop, your loop g, where you did some pretty weird stuff. But then f dot g is just you do both of them, where you first do f and then you do g, right? So this is going to be a binary operation. So now we're ready for a definition. Theorem. The set of what did I call our equivalence classes? Of homotopy classes. Classes of loops at base point x naught in some space x with the binary operation the product of the equivalence class of loop f with the equivalence class of group G, of loop G, is just the equivalence class of f dot G is a group. And we call this, it's going to be denoted pi 1 of the space with x point x0, and it's going to be called the fundamental group. Of x. Sometimes you want to best specify at base point x0. But seeing how time goes, there's some ways in which base point doesn't matter all too much. We might talk about that more next time. We might have to pick that up next time. But what I want to prove to you right now is that this gives you a group. And maybe before I do, like, just look at how this group works really fast. Like in this example, to make sure you have clear intuition on this. You know, if you take some, like, say, W2, and then you want to multiply it with, like, W minus 1, this says that should just be the equivalence class of W2 dot W minus 1. What is W2 dot W minus 1? Well, here, I go around W2 twice, and then what do I do after that? And I go back in the other direction, -1 times. What is that homotopic to? Why is it homotopic to W1? Because there's a homotopy where you can just start sliding this piece back, right? You can just take this piece right here and start sliding it back. And as you keep sliding it back, eventually you end up with the guy that just goes around once. So this W2 product W minus 1 is just itself homotopic. It's not equal to, but it's homotopic to W1. So this as a space is homotopic to W1. And you should take some time to convince yourself, in general, this is how the game works. That if you have some Wm and Wn, where m could be positive or negative or 0, that when you dot these together, you go around m times, or something homotoptic just going around m times. Then you just go back n times. That's equivalent to just going around m plus n times, which is exactly corresponding to the group structure you have on the integers with addition, right? So not only like is this like the integer, you know, in the case of the annulus, the fundamental group of the annulus S1 cross an interval at some base point, it's not just like analogous to Z, it's actually isomorphic to Z. This is what we're going to show next week. But hopefully now you at least have an intuition of that. But that's very different than like the story of, say, I don't know, let's say you're doing R2. If you're the fundamental group of R2 at your base point x naught, what is that isomorphic to? Well, it's just the trivial group, the group with just one element, right? So you can either call that the group 1 or the group 0, depending on your preferred notation. It's the group with just a single element in it, right? Okay, any questions on this? What I want to do is prove this, that this is in fact a group. So what does it need? What do we need to do to prove this? There's a technical bit of housekeeping to make sure that this is in fact well defined. If you pick two different representatives and two different representatives, that they're still going to be homotopic to each other. Not too concerned about that. The main thing I need to do to prove it's a group is I need to check that in fact under this operation I have the three properties that I have an identity. I have an identity. That it is inverses, yeah, and associative property. But I want to be mindful of time. So I think what I'll do is I'll pick up next week by proving this. For now, I think you have a good intuition of the fundamental group and how it looks for different spaces. I mean, one thing for you to muse about is what is the fundamental group of not just the annulus, but of something like the torus. Then we're going to have to come back and prove all these things. This is where we're headed. But what would it be for a torus? Because you can think in the torus, not only can you have loops that go around this way as many times as you like, you also have loops that can go around this other way as much as you like. Or you could do some combination of the two. You have loops that you know, in the process of going around this way, they then start I don't know, you know, all kinds of weird directions. And so what is a fundamental group of that going to look like? That's where we're headed. So next week we'll finish up the theorem, we'll prove that in fact this is a group, and then we'll prove formally that in fact the fundamental group for the annulus, or other things that look like the annulus, things that have a hole in the middle, is isomorphic to Z. Okay, we'll stop there.